Hi everybody, welcome back. This example 12.9 is another application of Kepler's third law. That is the assumption that gravity is going to be equal to the centripetal acceleration that is causing one body to orbit another body in a curved path. All right, and so we can say that t squared, our period squared, over our semi-major axis cubed equals 4 pi squared over gm. All right. Now what I did was the gravitational constant times the mass of the central body right there. That was part of g. I just took and divided it down, so it's on this side. All right. And the radius that was next to 4 pi squared that came from centripetal acceleration, I divided down over here. So I put the radius, or I should say the semi-major axis, at the bottom, and the time in the numerator right there. Why did I do that? Because for any system, this is basically a constant. All right, 4 pi squared is a constant. G is a universal gravitation constant. And M is that central body, the central, well, for our solar system, it would be the sun. All right, it's the central body in our solar system, or it's a body that is being orbited. All right. So we have a relationship between the orbital period and the average orbital distance that is some sort of constant for any body orbiting that central thing. All right. In this problem right here, we have some star, a star called S2. It's a very creative name for a star. S2 that is orbiting a mysterious object called Sagittarius A. All right, so this is a blow up of what's going on in that little teeny tiny spot right there at the center of our galaxy. Now, our galaxy is orbiting this whole area. All right, so therefore, you would expect this object, whatever this object is, that this star that you can see but the object you can't see, so right there is the object, Sagittarius A, a little green guy right there. This star is orbiting it in this very elliptical path. All right. So we want to find out the mass of Sagittarius A. So let's take this and shrink it down. And do that right there. We just simply want to find mass of S A. All right? So our period is 15.2 years. All right? So T equals 15.2 years. We need to convert that to seconds, right? So 1 year is 365.25 days. 1 day is 24 hours. And 1 hour is 3,600 seconds. All right, we're going to convert that to seconds. This star S2 that is orbiting this mysterious object, Sagittarius A. 15.2 times 365.25, just to be precise, times 24 hours times 3,600 seconds gives us 4.80. 4.80 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8th seconds. All right, that's going to be our time period. And a semi-major axis, A, we're told that as well. All right, so semi-major axis is 5.5 light days. It sounds like a period of time, but it's actually a distance. It's the distance that light travels in a day. So we've got 5.5 of those. Thankfully, it's already converted for us to meters, so we don't need to convert from light days or light years to meters. It's already done. But that's a very large number of meters. 1.42 times 10 to the 14th meters. So we want to find out the mass of Sagittarius A. All right, so this equation right here, this is a variety of Kepler's third law. Here we have our time and our time period and our semi-major axis on the one side. We want to solve for the mass, all right? We solve for the central mass. So the mass is going to be, let's see, 4 pi squared. So what I did was I brought the mass up right here. G is going to be in the denominator still. All right, so it's going to stay down there. And the A cubed is going to come up next to 4 pi squared, and the T squared is going to come down and be divided next to the gravitational constant, A cubed, like that. All right, so 4 pi squared That's easy to calculate into our calculator. We have an A of 1.42 times 10 to the 14th meters, and we're going to cube that. So that's why I'm putting it in parentheses right there. So that's going to be cubed, divided by the gravitational constant, 6.67 times 10 to the negative 11th. It's a negative 11 right there. Times our orbital period, t. That value squared. So 4.80 times 10 to the 8th. And that value is going to be squared. All right. So 4 pi squared times the quantity 1.42 e to the 14th. That's going to be cubed. All right. Divided by 6.67 e negative 11 times the quantity 4.80 times 10 to the 8th. That guy's going to be squared. And I think I have all my parentheses closed. 7.35 times 10 to the 36th kilograms is going to be our object right here. All right, it's a huge object. Now, as we get into 10 to the exponents right here, these numbers start to get really big that you can't really even comprehend them very well. But if you keep in mind that the mass of the sun is 2.00 times 10 to the 30th kilograms. This is times 10 to the 36th. That is an order of 1,000,000 times larger than our sun. Or I shouldn't say larger, I should say more massive than our sun. Also, keep in mind that in order for something, if something is 6 to 12 times the mass of our sun, so if you multiply that by 6, you get 1.2 times 10 to the 30th. Then the object becomes a black hole. All right, so only a few times larger than our sun does an object become a black hole. This is millions of times larger than our sun, so this thing is definitely a black hole, and it should be, because it's at the center of our galaxy. All right, it's the point around which all other mass in the galaxy is orbiting. So this is a tremendously massive object, most likely a supermassive black hole, and one of the most dangerous things we can possibly conceive of. So that is example 12.9, Sagittarius A, most likely a black hole, all found by using Kepler's third law. Thanks for following along. I'll see you on the next one.